Yeah, thanks everyone for joining for the second installment of our new IXSC seminar series. So today we have two really wonderful speakers. First, we'll hear from Jason McEwen. Is that right?
McEwen. Yeah.
McEwen, thank you. And Ari Savran. So Jason will be speaking first about science-informed or physics-informed machine learning, and I think how physics can inform machine learning, how machine learning is helping us inform about new physics. And he's joining us remotely from University College London, where he's a professor of astrostatistics and astroinformatics. So yeah, please take it away, Jason.
Fantastic. Well, thanks very much for the introduction and the invitation to speak here today. Yes, you kind of gave a nice overview already. So I'm subtitled this Machine Learning for Physics. So of course, how we can use machine learning for physics to learn more about physics, but also how physics can inform and improve machine learning models. So I've kind of cut this down from a slightly longer seminar. It's going to be very high level. I'm going to kind of just survey the landscape a little bit as I see it. I'm not really going to go into any technical details. I'll just discuss some kind of general themes and some kind of opportunities and challenges associated with those themes. But I will just highlight a number of works that kind of demonstrate some of the things I'm talking about, although I won't have a chance to kind of get into them in any detail. And of course, this is, a huge and rapidly growing body of research, which I'm sure everyone is doing a lot of amazing work in. So I can't possibly cover anything. Everything. I'm just going to pick a small number of examples. Finally, if you do want to know more, all the papers that I reference are hyperlinks in the slides, and the slides are already on my website. So if you're interested in digging into some of the papers that I referenced, hopefully those links can help you. All right, so let's get started. So as I'm sure everyone here knows, machine learning is a very powerful tool. And when you have a very powerful tool, much like a hammer, everything can look like a nail. So here we've got what I've called the machine learning hammer. It's kind of a general purpose tool or instrument. And yes, you can throw it at lots of problems. You can whack this screw with your machine learning hammer. You might have some success, but really there are much better kind of tools for the job. And so, I would kind of argue that, some years back, there was some of this kind of approach where we're just throwing machine learning at physical problems. But I think as a whole, the community as a whole now is kind of moving beyond this kind of approach to what I call the machine learning cog. So the machine learning is now one cog of many cogs to, which work together to do a more effective analysis, a more kind of nuanced and effective analysis for various data science problems. So what are these cogs? Well, as the kind of title suggests, obviously physics is a key component, how we can incorporate physical properties and physical models into machine learning models, but then also how we can link in with statistics and have kind of principled statistical frameworks and inference, and also how we can leverage and lean on kind of ideas from applied math as well and often integrate them. So this is the kind of outline of the talk. I've kind of called this physical machine learning or physical AI, for lack of a better name. And I'm going to cover basically three components. So physics-enhanced learning, how we can put physics into machine learning models. Probabilistic learning, where we can try and have a statistical interpretation of machine learning models. And then finally, intelligible AI. So I'm basically going to go through kind of each of these three sections. So let's start with physics-enhanced learning. So physics-enhanced learning, at the basic level, what is that? Well, we're really just trying to embed some kind of physical understanding of the world into machine learning models. So there's essentially three ways we can go about doing this: through augmentation, through integrating or embedding physical properties, or embedding full physical models. So I'm going to go through and describe each of these three. So probably the simplest way to incorporate physical knowledge in machine learning models is through augmentation. So we actually apply the physical transforms that we know the data must satisfy from the physical world, and we actually apply those transformations to augment our training data. So in this manner, machine learning models learn the physics through training. And in fact, this is common, for standard machine learning. It's very common, obviously, to augment data sets. Here we've got a cat, but it's augmented with a variety of transformations, rotations, flips, shifts, and other transformations. to basically augment, enhance our data set for these types of transformations we know the object must satisfy in the real world. Obviously, these are all still pictures of the same cat, but in different positions, essentially. Well, we can take this one step further, and instead of these being simple transformations for images, these can be more physically motivated or more extensive physical modeling, essentially. So one area where this has been done is for photometric classification of supernova observations, where our training data have very different distribution to our kind of test data. And so we'd like to augment that data, and where I would like to augment synthetic observations at different redshifts. So now our augmentation process is actually redshift augmentation. So we're applying basically time dilation type effects to synthesize objects at different redshifts. So we're kind of putting that physics into the augmentation. This actually helps in these cases improve performance significantly. But one downside of these kind of approaches is that data efficiency suffers. So in some sense, we've used the data to learn the physics rather than learning the problem at hand. So another approach to integrate physics into machine learning models is to encode physical properties of the world. So kind of fundamental base properties like geometry of data, or symmetries, or even conservation laws. So in these scenarios, physics is embedded typically into the architecture of the machine learning model. So again, this is actually done in traditional kind of classical machine learning. And it's one of the reasons CNNs are so effective, is that they encode what's called translational equivariance. So here we have an image. If we translate it and then compute some kind of feature representation, it's the same as computing that feature representation first and then translating. And this just means the feature space is very well behaved under this transformation and very effective to do subsequent learning on. So in some sense, even standard CNNs already do this. But we can maybe make this more specific for problems at hand that we experience in astrophysics and cosmology. And obviously in cosmology, we look out over the celestial sphere. If we have wide field observations, we can have observations over the full celestial sphere, like CMB. And so there, if we want to apply AI techniques faithfully for those type of data, we need geometric deep learning techniques defined on the sphere. So we need to encode that geometry. And it's not equivariance to translations that we need now, but equivariance to rotations. And we've been doing a lot of work on this space recently as well. There's some other really interesting work on equivariant machine learning by Villa et al., where they're considering the transformations that appear in kind of classical physics, with these group transformations on the right here. And again, focuses on kind of efficient methods for being able to integrate those. So these kind of approaches can be computationally demanding. Some might argue, are they always necessary? And yes, I mean, it is certainly true that they're computationally demanding. And I would say, that just means we need to put a bit of effort into thinking about how to do this efficiently. And that's precisely what we've been doing on the sphere for the geometric deep learning on the sphere, and also in that prior work I mentioned by Villa et al. And is it always necessary? Well, we're not actually enforcing these inductive biases. So usually, it can help a lot. And we don't need to perfect, the fact that for the CMB, we observe often through a galaxy, we maybe don't have CMB observations in the galactic plane. We don't have perfect rotational equivariance in our data, but that's also the same for standard images. So we don't have to enforce these inductive biases, but they can nevertheless still help a lot. So the third area, we can try and integrate full physical models inside machine learning models. So we can encode either the dynamics, physical dynamics, essentially through differential equations. And that's an approach called PINs, which I'll come to in a second. Or we can actually have a full physical model inside our machine learning model. And so in these approaches, physics can be learned both in the training and also embedded in the model. So with physics-informed neural networks, these essentially encode differential equations, typically through the boundary conditions. Automatic differentiation can be used to compute the derivatives involved. So that is one approach. Another approach is full differentiable models of our physics. Of course, as I'm sure everyone's very well aware, the way we typically train machine learning models these days is by gradient-based optimization. and we use automatic differentiation to get those gradients efficiently. So if we want to still be able to train our machine learning models in that manner, the physical models that we embed inside the machine learning models must be differentiable. We must be able to use automatic differentiation. So there's a number of works highlighted here. Some work we've been doing on imaging for radio telescopes, where we have a differentiable implementation of the telescope model. There's some interesting work on modeling the optical point spread function for Euclid in this manner, and some very interesting work by Jean-Eric Campagne and Francois Lanous and others on CosmoJax or JAX Cosmo, where they implement the kind of cosmological theory equations in a differentiable framework. So we need differentiable models if we're going to take this kind of approach. Also, we need differentiable underlying mathematical methods. So these models often rely on things like Fourier transforms, or if we're on the sphere in cosmology, spherical harmonic transforms. We've recently also been doing a lot of work on developing differentiable spherical harmonic transforms in JAX on the sphere. The paper for this should come out in a couple of weeks, but the code is already there if people are interested. So to summarize this section, pins in some sense only capture some limited loss. If we're going to have full physical models, we need differentiable programming frameworks. So, if we can do this kind of full approach where we have full models inside our physical models inside our machine learning models, I feel like, we've really captured a lot of the physics that way, but we need differentiability. One way we can address this is through emulators, which nominally would be introduced to speed up simulations, but the fact that these are usually implemented in a differentiable programming framework means we can also get automatic differentiation from them. Or we just have to write, some of these new differentiable codes like we and others have been doing. Okay, so that brings me on to the next section, which is probabilistic learning. So here we try and embed a probabilistic representation of data, of the models, and or of the outputs of those models. So I'm going to cover kind of three sections here. To start with, Bayesian neural networks. So with Bayesian neural networks, the idea is to quantify the uncertainty in their output. So we have a probabilistic representation of the output of our neural networks. This was an idea really pioneered by David McKay many years back now, but it was in some sense a bit ahead of its time, and we didn't really have the infrastructure or the compute resources at that point in time to really take this forward. But there's been a lot of effort in recent years to develop these kind of Bayesian neural networks. There's a number of approaches to implement this. One is through what's called MC dropout, where you consider having a probability distribution on the nodes of your network, and then you can drop those nodes with a particular, following a particular probability distribution. And in some sense, then you're sampling an ensemble of possible networks. An alternative approach is called Bayes by backprop, and there you now model the distribution of the weights, usually by a variational inference framework. And many of these methods are implemented in probabilistic machine learning frameworks like TensorFlow now, so they're very easy to pick up and apply. These approaches model the epistemic uncertainty of the model, or at least the part of the model that you've represented stochastically. Some might argue they encode the aleatoric uncertainty as well associated with your data, but that really depends on how you train the model and how you define your training data. So there's some caveats to be aware of there. I'd say a key thing for these kind of approaches is statistical validation, and I'll come back to this later in the talk. Another area of statistical or probabilistic machine learning is generative models. We hear a lot about these in the media, like ChatGPT for text or Stable Diffusion for images. So here, a generative model is essentially learned a prior distribution of our data. And then either we can use that for sampling and sometimes to evaluate probabilities. So a key use of generative models is emulation, where we want to speed up simulations. So I show a map here of a cosmic string emulation. So this is a component that could exist in the cosmic microwave background, but to simulate this requires something like 800,000 CPU hours on a huge cluster just to get one map. Whereas we can do this in a matter of hours on a single GPU now. Similarly, we can also apply these kind of methods to emulate the large-scale structure, again, over the wide field of views over the celestial sphere. And we have a couple of papers coming on these soon. We can also just, beyond emulation, we can also just take that prior distribution that we learn from data and include that as a prior in our subsequent analysis. So there's some really nice work from Benjamin Reme, Francois Lanus, and others doing this for mass mapping, where they learn prior from training data based on a diffusion model, or essentially learning a score, and then they integrate that into a MCMC analysis to recover mass maps, but also their statistical distribution. So for all of these kind of approaches, availability and representativeness of training data is absolutely critical. And of course, truthfulness, can we really, believe these kind of probabilities we get out of the model, or the diversity of machine learning models, which can sometimes be lacking. So we are getting more and more public data sets and benchmarks, which I think can help a lot with this. I'd say we're still maybe a little behind the machine learning community, but a lot of progress has been made there. Sometimes we can maybe introduce meta-sampling type approaches, which is what we did in this cosmic string paper by Matt Price and others, where we have some kind of meta-sampling to ensure we recover the right distribution over the data manifold. And of course, we need to validate that. We need to assess the truthfulness, and I'll come back to that. Finally, we can also try and enhance the accuracy and the computational efficiency of traditional Bayesian inference frameworks, and to such a level that we can maybe make approaches that simply just were not tractable in the past, we can make them then feasible. So one approach is to accelerate MCMC sampling to basically consider learned proposal distributions to help us explore parameter spaces. We've been doing some work on Bayesian model selection, where we have a kind of machine learning method integrated within a kind of statistical framework based on the harmonic mean, basically solving the exploding variance problem of the traditional harmonic mean estimator. And the nice thing about this approach is we only need posterior samples, so you can take any sampler. We're agnostic to the sampling techniques, which means we can leverage efficient samplers that, again, exploit differentiability. At the moment, we're working with using the NUT sampler and NumPyro, where we can get significant acceleration and also yet still do evidence. And we can also integrate this into variational inference approaches and scale to high dimensions. Simulation-based inference is obviously another area where there's been a huge amount of growth recently, where there you try to simulate your process rather than necessarily model it. And there, it's often also called likelihood-free inference, where you don't necessarily have an explicit likelihood and you learn that, or you learn the posterior. We've also been considering how to do model selection in this kind of framework, leveraging some of the techniques I talked about previously, like this harmonic approach, which, by the way, harmonic is the name of the code as well, which is publicly available if anyone's interested. And of course, there's variational inference approaches as well, where we can try and assess the uncertainty associated with the outputs of machine learning problems. So availability and representativeness of data is, again, critical in this kind of setting. Cost of training can sometimes be significant, and obviously truthfulness is absolutely critical. This is kind of a running theme that we're going to get to in just a second. As I said already, public data sets and benchmarks are helping with this. In many cases, we can amortize inference, so we only need to train once, and then we can apply it over many new observations, so that mitigates the cost of training. If we can also integrate these techniques in an overarching Bayesian framework, we can often leverage the statistical guarantees that come with that framework. So this is also a great way to kind of enforce some kind of truthfulness and validation. But nevertheless, we need to do, I think, more extensive statistical validation as a community. Okay, so that brings me to the final area of these kind of three topics, and that is intelligible AI. So I've split this into explainability and interpretability, which actually, I view as slightly differently as I'll go on to explain. Sometimes these terms are used interchangeably, and also truthfulness. But fundamentally, what we're getting at here with this overarching theme of intelligible AI is machine learning methods that, in some sense, can be understood by humans. So what does that mean? Well, explainable machine learning techniques themselves may not necessarily be interpretable, but the idea is that their outputs can be explained to humans. So, a traditional thing that can be done there is maybe look at the feature importance, the importance of different features that go into your machine learning model, and try and see, how important are those different features. Another approach is saliency mapping. Here we have images of galaxies, and we're trying to automatically determine the morphology of galaxies, but one would like to ask, well, what was it in the image that suggested there was a bar or there was spiral arms in the galaxy? So there's some interesting work by Prab Brambra, Ofer Lahav, and Benjamin Yokimi doing this for galaxy morphology. And yeah, you're basically recovering heat maps or saliency maps to show what are the components of the image driving classification of certain components. These kind of approaches, though, in a sense, we're probing the black box. We don't actually understand the black box. We can't really look inside it, but we're trying to get some kind of explanation of the output. But we're still not really able to understand or comprehend the underlying process, which is, I would say, a limitation. So this is where I make the distinction to interpretable machine learning models, which in this case now are white boxes, and we can understand the method itself, not just try and understand its outputs. So there are a number of ways, we can attempt to try and construct machine learning models that are white boxes, one of which is designed models. So for example, scattering networks and wavelet phase harmonics kind of mimic the structure of convolutional neural networks. There's convolutions followed by nonlinearity and then kind of cascading transforms, but we don't have filters that we learn. The filters are very prescribed, are wavelets essentially in these approaches. And these have a lot of nice mathematical properties that we can then show a lot of nice properties for the overall network. So we can kind of study the properties. We know like what the filters are. We're not actually trying to learn. And then we can also
Jason,
localize.
just to let you know, you're at 25.
I'm at 21 on my clock.
Oh, no, sorry, you're at 21. You're at 12:25 is the time.
Oh, okay, yeah. So I'll just wrap up just another couple minutes, if that's okay. So we can also localize on the sky the kind of components, driving features of these kind of constructions. Also, we can try and impose other constraints on machine learning models. In fact, one thing we've been considering recently is to impose convexity, which is quite a big constraint. But then this, again, we have very nice mathematical framework. We can leverage a lot of statistical theory around convexity as well. And we have a paper coming out on this soon. Again, we can make use of our training data to essentially provide a prior. And so, we have a much clearer idea of, what is the machine learning model representing? Well, it's really just a prior, and that's encoded in the training data. And we can relate that to the corresponding machine learning model. So we've been doing some work in this on the proximal nested sampling with learned data-driven priors, where we can also compute the evidence to do model selection for imaging problems. So design models like this do limit flexibility, but actually we've been pleasantly surprised that actually the reduced flexibility has a minimal impact, we've often found, and in many cases is far outweighed by the advantages you get. In the interest of time, I'll skip on to the last section, which is truthfulness, which is obviously absolutely critical for science. If we want to do scientific analysis, we need to have a meaningful statistical distribution of our outputs. So, not only do we need, accurate outputs, but we need outputs where the statistical distribution is meaningful. So this is an example from Hermans et al., where they do very extensive statistical validation tests for simulation-based inference. And, in this case, a machine learning model gets similar performance, but has a very different distribution. And so, what we need to not just consider how effective the method is, but is the distribution valid? In Lemos et al., they again present some methods for doing coverage tests, so we can see are these so-called probabilities that we get out of machine learning models actually reflective of probabilities if we run many experiments. I mentioned briefly already, diversity can be a big problem for machine learning models that can suffer often from mode collapse. How do we ensure that we can recover a distribution over the full underlying data manifold? there's some work we've been doing to try and address that. So to summarize, uncertainties are not always meaningful. Diversity of machine learning models can be lacking. We really need to do extensive validation tests, but we also need to, if we can really integrate inside a statistical framework, then we can inherit all the theoretical guarantees of that framework. Maybe sometimes we can introduce meta-sampling approaches to address some of these problems. But if we can introduce kind of well-posed frameworks where it's enhanced by our physical understanding, it's probabilistic, that can also help a lot. So that brings me to my final slide. Obviously machine learning is a very powerful tool. It gives us a great deal of power, but with great power comes great responsibility. We've got to use machine learning in a responsible manner. And I would advocate the way to do this is with this kind of machine learning cog approach, where machine learning is one cog of many, and we can, these cogs can work together to provide us kind of accurate, principled, interpretable analyses that we can trust. Thank you.
Thanks so much, Jason.